Hello, my name is Abdul Lakosha. My group members are Clifford Ojukanaye, Karim Al-Darbi, Kurtian Yan, and Ziad Suleiman, and we are presenting renewable energy and its impact on supply chain. We are focusing on generation of power and heat through biogas. According to the United States Energy Information Administration, renewable energy is defined as energy from sources that are naturally replenishing, such as wind, solar energy, geothermal energy, hydro energy, tidal energy, and biomass. These energy sources are virtually inexhaustible but are also flow limited, meaning that they are limited in the amount of energy available at an instance of time. According to the Institute of Procurement and Supply, supply chain management is defined as the handling of the flow of goods and/or services from the raw materials, from supplier to manufacturer to retailer to customer. This requires the company to have a network of suppliers to move the product through each of these stages. We are focusing on biogas for this project. Biogas is a blend of gases produced by the decomposition of organic matter in the absence of oxygen. As for the process of creating biogas, feedstock of solid and liquid organic waste from farms or homes or industrial facilities are fed into a digester. The biogas then flows upwards and is collected. At the same time, the residue is also collected for use as a fertilizer. This is called the digestate. The digestate is separated into animal manure and vegetable waste. These are photos of both types of digestate, the animal manure and the vegetable waste. This is an anaerobic digester which uses a large tank as shown in the photo. This is a diagram of the process for the anaerobic digester. You can see in the photo that both the biogas and the digestate are produced by the digester. This diagram shows more detail for the use of the actual biogas itself. We can see that after the biogas is processed, it is then refined using gas cleaning. To be used in place of conventional gas, it is purified and then transformed into biomethane. To be used for electrical or thermal energy for home heating, this product can be used in a heat generator.
Where is renewable supply chain management? Renewable supply chain management is the management of material, information, and capital flows, as well as cooperation among companies along the supply chain, while taking goals from all three dimensions of sustainable development. The main goal of using renewable supply chain management is to increase the techno-economic and environmental status of the supply network. Different forms of energy are used from the supply of raw materials to manufacturing and finally to the distribution process. Examples of these energy sources usage are power generation, heating, cooling, and transportation. Benefits of anaerobic digestion. It includes three major categories, which are environmental benefits, energy benefits, and economic benefits. Examples of environmental benefits would be productions of sanitized compost and reduction in pathogens. Examples of energy benefits would be production of high-quality fuel and reduced reliance on energy imports. And finally, examples of economic benefits would be increased self-sufficiency and reduced water consumption. Continuing about anaerobic digestion in farm usage and sites. These include the combustion of methane to generate heat or power. In addition, anaerobic digestion takes part in the substrates consumed on farms as fertilizers. Finally, the carbon dioxide product can be used as a source for the plant production. Moving on to stages of the renewable supply chain management. The following figure shows the general pathway of the process. It begins with the suppliers, to the manufacturers, to the customers. From the figure shown, it can be concluded that renewable energy has the capacity to power all aspects of the supply chain, for power, heat, generation, for domestic, commercial, and industrial uses. Three main challenges emerge from implementing renewable supply chain management. Starting off with the strategic, which include long-term plan, for instance, plant location. Next, tactical, which is a medium-term plans like buying material and decisions about production. And finally, operational levels, which are short-term plans that are daily scheduling.
The challenges of integrating biogas using renewable supply chain management include using new strategies for plant location, as well as using new strategies for transportation, inventory, sourcing, information, and system variation, as well as other considerations when using biogas, such as potential health issues and scheduling issues. This is a summary of the challenges of renewable supply chain management in general. These challenges include challenges at the supply level, production level, distribution level, and the demand level. A question for us is, what proposes the greatest impact on the supply chain? The answer is the tactical level, meaning the transportation strategies, marketing, purchasing, as well as the production. This is because we need to know where to source the feedstock from, and we also need to know the quantity of electricity or heat to produce to satisfy the customer's need over a period of time. We want to make a mathematical model of the impact of using biogas on supply chain management. We create this model based on sample numerical data of heat and power generated from using biogas, as well as some assumed data. The next slides cover the result of this model.
In this mathematical modeling, we have total solids as Ts, volatile solids as Vs, retention time as RT, total solid waste as TSW. For a sample bench type digester to calculate its volume, assume average weight of feedstock for digester is 20,000 kilograms a week, which is around 2,860 kilograms a day. The total solid waste is 286 kilograms. We have bench size of 3,575 liters. The retention time of digester is 25 days. The required digester volume is 89,375 liters. So we have volume of 80 tank around 290 cubes. In organic loading rate, we have total solid waste of 286 kilograms. The volatile solid is of 257.4 kilograms. So that we have our organic loading rate of 2.86 kilograms Vs per cube per day. The methane yield assume a digestion yield of 80% methane. So we have Vs converted around to 206 kilograms. Assume biogas density is 1.14 kilograms per cube. So we have around to 181 cubes. Assume methane is 70% of biogas. So that we have 126.7 cubes.
We can calculate the methane yield by dividing the volume of the methane over the Vs in methane, which is the mass of the methane. It is equal to 126.7 meter cube over the 257.4 kilograms. It is equal to 0.49 meter cubed. Then we can calculate the production rate of the methane. It is the volume of the methane over the volume of the tank. It is equal to 10.3 kilowatt hours over meter cube. So now we can move to the amount of energy if we are assuming that the methane biogas yield from the source is equal to the natural gas equivalent. So we can calculate the energy yield using the volume of the methane per day, and then multiplying it by the production rate of the methane. It will give us 4,687.9 megajoules. After multiplying that, if we are calculating the heat generation from the combined heat and the power plant, we are assuming that 50% of the energy yield per day is converted to useful heat. It is the 50% times the energy yield we calculated. It is equal to 2,343.95 megajoules, and the other 30% is converted to electricity, and the rest 20% is linked to the losses in the system. And we are then getting the heat generation from the boiler. We are assuming that 80% of the energy yield per day is converted to useful heat.
So we will multiply 80% times the energy yield we calculated. It is 3,750, and we can move to the next part now.
When examining the mathematical model, we go into two case studies, one in the UK and the other in Canada. For the UK plant, it's a co-digestion plant. That means a plant that is being fed by animal and plant waste. It generates about 450 metric cube of biogas per day, and the gas is being used to generate 18.22 kilowatts of electricity for a 19.5 hours operation per day. And the heat generated is about 30 kilowatts of heat. The following table shows the financial, which consists of the capital and running cost, as well as the annual income of the plant. The payback period for this plant is 4 years, as it generates about 73,000 pounds per year. In Canada, the plant is in Leamington, Ontario, and it's processed about 30 tons of waste per hour, which generates about 100 metric tons of 100 megawatts of electricity per day. The following table shows the summary of biogas plants in Canada, as well as energy produced from them till date. We go to the recommendation now. Supply chain managers and researchers should increase their visibility in the renewable energy sector. Staff should be trained to understand the benefits of adoption of this technology, and good information and management system should be in place that will integrate all the activities of the supply chain from suppliers to customers. Finally, sources of inventory, buffer stock for the technology should be studied as well. Thank you. If you have any questions, please let us know.